K, low, high. Low,
Oh yeah, the table. Yeah. Yeah. Yeah, sure. Did you watch my video?
Of course.
Awesome. Did you like it?
I didn't do that.
Oh, Chrissy. Right. Now. Oh, what's going on here? So we'll continue with the photoelectric effect. Do you remember what that was?
Yeah.
What?
Oh yeah, electron heat. Photon heat.
The metal surface, yeah. It frees an electron. And vice versa, which I think is interesting. We said when the electron hits the metal surface, it releases a photon, which is quite interesting. So, on to a little bit of conservation of energy. So let's imagine we have the electron trapped here, and we have our photon here. And it's coming in, and it hits this, and then out comes the electron. Okay, so if I draw a line here, in the before picture, what is the energy? It has kinetic energy. Whoa-ho-ho! Okay. It has kinetic energy. And what type of energy does this have? This trapped electron. Negative potential. And what did we use as the symbol for the potential, negative potential here? Do you remember it was the work function, the phi? So this has energy of minus phi. And why is it minus? It's trapped. So in total the energy here, oh no, hang on, guys, we're being stupid because it's early. What's the formula for the energy a photon has? HF. And here is minus phi. And the energy here? Kinetic. Now, if we want to be technical, it's a maximum kinetic energy because some of the energy could come out maybe as heat. So this is the most kinetic energy it could have. But maybe there's other forms of energy released after the collision, like heat or whatever. So some books like to write KE max. I don't like to write the max, but I want to tell you this because in the exam they may write KE max, and sometimes the word max confuses people. They mean like, oh, do I have to use calculus or something? No, it just means the kinetic energy if nothing is lost in the collision, that's all. So, if we equate the two, we have the formula HF minus work function equals KE, which is what I have here, but you actually more usually write it like this, where everything is a positive in the formula. So, we bring this to the right, and we end up with the formula HF equals KE plus the work function. And that's, a simple formula that, it just comes from the conservation of energy. I hope that makes sense, yeah? Shall we continue? Yeah? Okay, so, continuing. By the way, this is what Einstein won the Nobel Prize for, the photoelectric effect. So, in other words, this formula, not the E equals mc squared formula. Right, here's a short little question. The work function for copper is 4.7 electron volts. A photon of wavelength 250 nanometers strikes the metal surface. After the photon hits the metal surface, an electron is freed. The first question is what is the work function in joules? So convert that into joules. And the second one is to find the V. So you need to use this formula. Except, do I give you the frequency? No, I give you the wavelength. But that's super easy to fix because you can just change this into hc over lambda equals, and this is a half m v squared plus work function. So by using this, you can quite easily get the v. Okay, so let's give you a minute to calculate this. Shouldn't take you too long, it's not so difficult. Come on, bread boy. What's taking so long? Do you like wake up at 9 o'clock? Or even after 9 o'clock? Like, be honest, what time did you physically get out of bed at?
Around 9.
Which side of 9?
I don't know.
I think this morning? Pre or post?
Pre-9.
So it took you 15 minutes to get ready.
I need time.
So you look like this. So you must look awful when you wake up that it takes you 15 minutes to get ready.
Wait, what does this mean?
How does it take you 15 minutes to get ready? Yeah. Are you doing your hair? Your makeup? Or what's...
My lens.
Goodness.
All you did is use the same topic as last one.
Look, just eat your bread and melt this down, please. We're continuing. Do we have answers? Sean, answers yet? No? The formula you'll need to copy from someone that you missed that we just did.
In that short time.
What do you mean that short time? It's 9:15.
Only one.
Exciting, we're nearly finished the physics course. I think there's just one topic after this. Yeah. Then we can start our revision.
How to convert EV to
You know this, my friend. You know this. Don't hesitate.
I don't want. Divide by Q. Divide by.
No.
No. So.
E, yeah.
I mean, same. In my calculator,
Charge of electron.
Type exponential.
No, don't. You're lucky I'm too tired and hungry to come over to you. Have we got the first answer at least?
Yes.
The first one is 4.7 E. Is E 27? No, that's all. This is the first one.
FY.
Huh?
What do you mean? Yeah, what do you mean why? 4.7 E. Yeah, joules. Joules. No, don't. This is simple. 4.7 times E. That's how you change electron volts into joules. There should be no questions. This is not a hard thing. We've done this many times.
It's confusing.
No, it's not confusing. What's E? What's E? Charge of electron.
It's operating.
Oh.
Come on, guys. Come on. Come on. And the next one is what's the V? So
Yes.
I can use the formula here to get the V. If I just do HC over lambda minus the work function over a half m square root. That's going to be the V. So let's do that. Square root fraction. What number is the mass of electron on the calculator? Is it 3? Yeah. And then what number is Planck's constant on the calculator? Who has Planck's constant, please? 6, okay. And the C, 0? Okay. And what did I say the wavelength was here? 250 nano. Okay. So the speed of the electron that's released is, let's put it in kilometers per second, 302 kilometers per second. 302 km per s.
Fast is this?
Ferry. You know how long a kilometre is? Can you imagine 300 kilometres? 300 kilometres is like the length of Ireland. It can do this in 1 second. Yeah. Dublin, no, it wouldn't even be Dublin to Cork, because Dublin to Cork is only like 200 kilometres. It'd be the length of Ireland. Yeah. Yeah.
How Einstein got this?
What do you mean?
Like, it's very fast, and to get Nobel Prize is to be proved as experiment.
Yeah.
They have
Yeah.
to see the photo from matter.
Maybe he did it the other way around. Maybe he fired. It's probably easier to fire the electron at the metal, because when the photon comes off, you can easily measure its wavelength using some kind of spectrometer or prism, because the wavelength's just a colour. And it's easy to know the velocity of the electron because you can put into an electric field. And if you know the strength of the field, you can know the acceleration. And if you know the acceleration, then you can know the velocity. So I would imagine to do this experiment, it's easier to prove it backwards, that an electron with a given speed will make the photon appear with a certain wavelength. I don't think that's too hard to do. But I do agree, it's probably hard to do it the other way around. But actually, maybe not, because what you would just need to do is, if the electron comes out with this speed, you would need to put it into an electric field in the opposite direction to slow it down. So you would need to make the electric field strong enough to bring this to rest. And then if you know the strength, you can know the deceleration, which means you can know the initial velocity. So maybe it's not too bad. Not too bad.
Can I do the calculation?
On the calculator, sure. Oh, perhaps it's gone. This?
Yeah, let's check.
Yeah. Continue? Yep. Okay, so let's have a look now at something else. Oh, come on. Right. So we have this idea called threshold frequency. When we shine the photon onto the metal and it frees the electron has a kinetic energy. But maybe we don't want the electron to have a kinetic energy. Maybe we just want to free the photon just enough so it's freed, but not that it's moving very fast. In other words, we want to know the limit. What is the energy I need to just about free it? So it's barely moving. Do you understand? This is called like the threshold, the limit, the minimum energy to free it. And if you think about it, you can get it from this formula, because it just means that you don't want a kinetic energy, really. In other words, you want this part to be zero. So that means the frequency, the minimum frequency you require, is the work function divided by Planck's constant. So if it has exactly enough energy, it'll just about be freed. That is, you can get this formula here. This is called threshold frequency. It's the minimum frequency to free the electron. So just work function divided by h will do. It's the threshold frequency is the minimum frequency required to free the electron. Again, what is this reminding you of in chemistry? What is this like in chemistry? It's like ionization, isn't it? The ionization is, what's the definition? Do you say it's the minimum energy required to free the electron, or what do you? You don't use the word minimum. But technically it is the minimum. It's the least energy you need to free it. Yeah? You got that formula? Continue? Yeah. Where is Jerry? I had a very important message for him from Isabel. Isabel is very angry at him. If you're watching this video, Jerry, Isabel is very angry at him because he hasn't submitted his application yet.
He's doing that right now.
Oh, that's why he's not here.
Yeah, he's done it. Yeah, so but who is our reference letter? Tutor.
Jerry. We got this? Continue? So, the work function for gold is 5.1 electron volts. What is the threshold frequency? Alright, well that's easy peasy. What's the formula? Yeah, work function, which in this case is 5.1 E, over H. What is H? Did we say 7 or 6? 6. I mean on the calculator. So, the threshold frequency is this. It's the minimum frequency. Okay? If the photon has twice the threshold frequency, then what would be the kinetic energy of the free electron? So, now for the second half, we have gold, and we have our electron, and the photon here, the F will be twice this. Okay? So, what's our formula? HF equals KE plus work function. Now, this is the answer. Now, in fact, I don't really need this answer for the second part because I can do a little trick here. Because I know that this F is going to be twice the threshold. And what's the formula for the threshold? It's work function over H. So I can actually kind of take a little bit of a shortcut on the calculator because I can delete these, cancel these. I can take this over to the left, so I get one work function. Yeah, and that's equal to a half mv squared. So the v in this example would be twice the work function divided by the mass square root. So actually, I don't even need this answer. So let me just hit this in. Oh rats! What was the work function? 5.1. Where's my 2? Oh, 2 work functions minus the work function. And then constant number 3 for electron, and the velocity will be that, which is 1,339 kilometers per second. Kilometers per second. Now, this sounds very fast, and it is very fast, but remember, the moment the electron is released, it'll probably hit into something. It might hit into a molecule of oxygen or nitrogen. Even if it's in a vacuum, eventually we'll get to the end of the vacuum and hit the glass container. So, although it's very fast, its speed is only going to be this briefly. So eventually it'll hit something. Oh, I didn't even ask for, I just wanted the kinetic energy, not even the speed. So I could have actually just, I could have stopped here. The kinetic energy is equal to the work function in this example. So, in fact, the answer for part B is 5.1 electron volts in this example. So what? Doesn't matter.
Even if it's twice.
Yeah. I just worked it out here, see? The kinetic energy is equal to the work function in this example. So, therefore, 5.1 electron volts.
Should I always change the electron volts to
You don't have to. Sometimes they ask you to. It's good practice to use electron volts when you have very small energy levels. The energy levels here are very small. Electron volts will be suitable to use. But it's like saying, should I use micrometers? I'm like, well, you know, if it's a small measurement, you should, but you don't have to. It's fine not to. But if they ask you to, you definitely should.
You change the exam.
If it was me doing the exam, personally, I would change it. But in fact, the marking scheme has no expectation that the student would change it, and they would leave it as 10 to the minus whatever. It's just, I like using prefixes, you know? It's my pastime. Students don't like using prefixes. I think this is a shame. Is this a good question?
No.
Okay.
What's the answer for the first one?
I don't know. There it is. Yeah. What is it? 6 mega, 9 giga, 12 tera. Is it like 123 terahertz or something? What? Okay. K is right. Continue. So here you go. There's your 3 questions for this lesson. This might be slightly different to the one that's online because I made a change to question 3. I remember because I made up a material in it called stevinium. Right there. Stevinium is a great material. It has a very low work function. Yes. I can make up my own materials if I want. What? Stevinium. Not heard of this? It's amazing material. What happened was I was trying to find a material with a low electron volt work function, and I couldn't find one low enough, so I just made up a material. Yes.
What is the formula, what is the unit for triphone frequency? Hertz?
Say what?
The triphone frequency.
The threshold frequency, hertz. Part 3 is an interesting question because the first part of it is you actually get to calculate how much energy a 10 by 10 centimeter solar panel made from copper would produce. So if you had a little 10 by 10 centimeter square of copper and you want to use that to make a solar panel, you can actually work out how much energy that is and what the current is. You might be disappointed by how small it is. I don't even know if it's a millicoulomb amps. It might only be a microamp. Huh? Well, it's bigger than what's on your calculator. So we're missing Jerry. That's it.